So in this video, we're going to look at the concept of the condition number, because we are looking at linear systems. We've been looking at them, and now we need to start looking at how do we actually compute the error. How good is our solution? Even in the direct methods, as you would have seen in scaled partial pivoting or partial pivoting, why is there a need to have these? Is because we clearly see that there is, even in direct methods, our solutions are still approximate. They're not in fact exact. So this means, not in the absence of the exact solution, how do we actually get an idea about how good or bad is our solution? To answer this, this is where the concept of the condition number comes in. Now, in order to get to the condition number, let's define certain things for the sake of getting to that definition eventually. First of all, we'll call x hat the exact solution, okay, for the purpose of this video. So x hat is, in fact, we call that the exact solution. So of course an underline under it, meaning that it's a vector. So this is a vector. Now remember, our target is we are solving the system ax equals b. And let's say that x bar is our approximation, okay, our approximate solution. So we'll call this our approximate solution. And of course we know that ax is not necessarily equal to b because our solution is approximate. Then how can we, in the absence of the exact solution, how can we know how good or bad our solution actually is? For this purpose, we define something called the residual. Okay, the residual. And the residual is basically a very simple idea. If you think about it, how can we judge the solution that we have? Very simple. We have the right hand side and we have the system ax equals b. Now, if I were to look at what is the difference between b and ax bar, that should give me a reasonably good idea about how good or bad my solution actually is. Now, in order to look at this symbolically, is there actually a relationship between the error and this? Let's look. So I'm going to put a box around this. This is the definition of the residual. How we calculate the residual is we take the right hand side and subtract off from it a times our approximate solution. That gives us the residual. Now, let's have a look at a little bit more detail in this. Now, if x hat is the exact solution, then clearly ax would equal exactly b. It would exactly equal b because this is the exact solution. So it should satisfy the equation perfectly. And therefore, ax hat should be equal to b. Which means that I would be able to just do this, which is replace here the ax hat. And of course, then I just have this equation revised, which means that this would actually equal, if I take the a out, x hat minus x bar, our approximation. And now if I define the vector epsilon as my error, then clearly the error, in fact, which you can even see here by definition, is the difference between the exact and the approximation. Interesting relationship. Notice here this very interesting relationship, and the relationship is that r, in fact, seems to be equal to a times epsilon. So I want you to note that. Now, that's not how we compute practically the residual. Keep this in mind, please. This shows us that the residual is in fact this matrix, our coefficient matrix A times the actual error. And the error is what? The error is the difference between the approximate solution and the exact solution. Now, we don't have epsilon because we don't have the exact solution. But we do have, and we are able to compute the residual. So the residual, therefore, in theory, should be able to give us a pretty good idea about how good or bad our solution is. Well, you'd think that, but there is a disease that exists within systems of equations, and that is called ill-conditioning, or ill-conditioned A matrices. So, in other words, this matrix A could be ill-conditioned. So, in theory, if epsilon is small, okay, that clearly would indicate that R is small. But is the converse true? What can we for sure say that if R is small, what can we say about epsilon? The problem is not always small. And this is a very important problem for us to tackle. Now, of course, I'll show you by example, in fact, how this, in fact, doesn't work, or the situation where it doesn't work. Let me show you with an example. So here's an example of a system ax equals b that we want to solve. Now, if we use Gaussian elimination in this particular matrix, one iteration of Gaussian elimination would give us this. So as we eliminate this here, we'll make it 0. What happens to the 0.1441 is it becomes 7.7 into 10 to the minus 9. Now that's a very, very small number, in fact. That's almost showing that this matrix A is almost singular, in fact. And a singular matrix means the inverse doesn't exist. So here, let me just go further and say that in this case, when I solve this system, when I go further and solve the system, okay, it turns out that the approximate solution, okay, and you can check this yourself. The approximate solution turns out to be this. Okay, this is the approximate solution. And now, since I have the approximate solution and I have the A, I can calculate the residual, which is B minus A times this X, this one here, and this A here, and this B here. I take these three, B minus AX, and when I calculate that, turns out that's equal to 10 to the minus 8, and this is almost 10 to the minus 8. Now, that's a very small residual. That's a small residual. Okay, that's a small residual. Now, if I go further and actually look at the exact solution for this happens to be 2 minus 2. You can check that. Look at our solution. Our solution is here. This is our approximation, and this is the exact solution. The error, okay, in this case, the error in fact is this, okay? So as you see, that's a pretty bad error, in fact. So a small residual doesn't necessarily imply a small error. Now, what's wrong with this matrix? If we look at this matrix a bit more carefully, if I go back to the point I was trying to make, if you look at this number here, this is the culprit, or in fact, this is the culprit. Very small changes in this number can lead to very large changes in the solution, in fact. And such a matrix which is almost coming down to be where A is almost very nearly singular, we say that A is ill-conditioned. Ill-conditioned. Now we need to elaborate on this idea. What is this condition, this ill-conditioning that we're talking about? Well, in order to look at this, we need to look at some more preliminaries, and then we'll proceed to calculate, in fact, what we initially referred to in the title as the